I'm here to introduce Irina Rish. She is a researcher at Mila and leads the Autonomous AI Center. She has previously worked with IBM as a researcher and has 64 patents in her name and over 120 research papers. So give it up for Irina.
Thank you. This is an amazing venue and everything, even despite the rain. It's been like a great experience so far. And okay, I'm going to talk about scaling today, but it's more of a informal talk discussion. So please feel free to interrupt with questions even during the talk. And it's more like thoughts about a bit of a history, like where the scaling kind of came from, what was the role in the recent years in AI, as we all know, where it's going, or maybe what should we do differently. So it's a bit like open-ended discussion. Yeah, so I'm probably going to be skipping a bunch of slides because but yeah, feel free to ask questions as we go. And I guess at the end, hopefully, I will leave at least 15 minutes for discussion, right? And please show me when the time comes. Okay, I'll try to be quick. So indeed, talking about AGI, we can focus on different aspects of that, and there are as many definitions, I guess, as there are people, but you can focus on the G, general, and interpret it literally. And you can basically say that, okay, so the whole history of AI, machine learning, and before that statistics was about generalization, right? So basically any data analysis field that was trying to make inferences and predictions just wanted to generalize to examples out of distribution. Yeah, so basically it's just as old as the field of statistics. And of course in machine learning, things progress kind of rapidly to going further out of distribution. The very hot topic that was, still is, it's just large-scale models seem to be now so much better. But like 5 years ago, out-of-distribution generalization was extremely hot research topic. Many people, including people at Mila and our group, worked on this follow-ups to invariant risk minimization approaches. Bottom line, when machine learning methods will be trained on some data sets, the proverbial cows on the green grass, and the model will not generalize to detecting cows on the beach, for example, because it's like a lazy student that studies to the test, it picks like spuriously correlated features that are easy, like background, and then of course it does generalize, and people were like coming up with all kind of algorithmic improvements and this, how to deal with it. Only to observe a few years later that if you start scaling models and get prediction models, they kind of seem to take care of that without any specific sophisticated algorithms. So that was kind of interesting little lesson to many researchers. Similar thing with adversarial robustness in the sense, okay, that's harder, and I think there will be talks about that today. But you also kind of can view it as generalization out of distribution. It just the shift is not innocent statistical change. Sorry. But what I'm trying to say is that the generalization is pretty much in various ways the goal of any part of machine learning, whether it would transfer or continue or domain adaptation. It's always been there. So when we talk about AGI, again, there is a whole spectrum of how we can talk about that and what we mean by that. And people go all the way to thinking about conscious machines, or you can be very pragmatic and say, hey, it's just like generalization out of distribution taken to extremes. So the tasks and distributions are really very, very broad, and hopefully at human level awareness. And again, so you may say I'm completely agnostic about other properties of the system, consciousness, intentions, or whatever. I don't know. It's just extremely out of distribution working kind of machine. And then, again, completely hypothetically, as I said, it's more of a discussion than brainstorming. Like if you think about like how you can get to extreme generalization, broad intelligence, why very large-scale foundation models might be getting there. One common hypothesis is so-called like compositional generalization. So imagine a very simple case. You're basically trying to learn autoencoder, like linear autoencoder, very simple thing. So essentially, you're trying to learn PCA components of some linear space. And imagine you keep getting more and more diverse data. So you keep covering different parts of your humongous space of data points. If you sample your data properly and it's sufficiently diverse, and you've got enough of that, you probably at some point will acquire all of the principal components of the world that are enough to pretty much represent everything sufficiently accurately. Assuming that the world is very high but finite dimensional. So things can be represented by combination of some large but finite number of elements. It's all hand-wavy, but what I'm trying to say that perhaps it could be one of the reasons why scale with data and diversity of the data and the corresponding model size, so it can incorporate all this information, why it may get us to kind of at some point grasping all the principal components of the world. And you can say, well, that's kind of where you can claim you have something like AGI. Again, it's just more of a way of thinking about what might be going on, but it's quite hand-wavy. And of course, in neural networks, it's not just, it's not SVD, it's not just a linear autoencoder, it has to learn functions, and it should be functional space, and so on and so forth. But you can say that in a sense, with human history or kind of living world history, the networks evolved to have like a finite size network that does seem to capture major components that, when they combine, allows that network to act and survive in the world. Anyway, as I said, it's more of a conceptual way of trying to think why scale, if done properly, may lead to this generalization. And of course, yeah, we all have seen that. Like, boom, in 2020, we see GPT-3, just scale increased, pretty much no sophisticated algorithms added, nothing, and it starts generalizing out of distribution, kind of a few samples, and doing tasks it was never trained on. A year later, 2021, the paper on foundation models, like surveys, was going on in the field. Yeah, you all have seen that. Essentially, it's, again, nothing new algorithmically or conceptually. It's unsupervised, pre-trained models just on extremely large, diverse data sets. So you can sample the distribution well and maybe get your principal components, quote unquote. And the model scales too, because you need capacity to incorporate this information content. And it keeps going on. In a sense, like we all probably have seen this quotes from Peter Lesson that, in a sense, it's not the first time in history of AI when scale is like a central element of success. Because the whole history of AI, in a sense, was from more man-made, handmade rules, expert systems to machine learning, then manually constructed features for images or speech or sound replaced by, well, automatically learned features, deep learning. So things go in the direction of further automation and eliminating human out of that loop using something generic that scales. So it's not the first time we see that trend, right? And in a sense, I mean, that's, I guess, what humans always wanted to do. They want to get lazier and lazier, so things kind of evolve on their own, and we only see kind of particular period in that history right now. So scaling, at least scaling laws, or in any case, like scaling behaviors, they have various, there are various reasons to looking at those. And one of the reasons, well, besides trying to predict for a particular approach, like how well it's going to perform if you keep investing in compute and add more data and this model, it's what can be called like an investment tool for machine learners. If you have several methods that you want to compare, historically they were just doing it for given data set, for given benchmark, instead if you compare trends, you may see that the performance reverses and say vision transformers were not so good at smaller data scales, convolutional networks were better, and then the situation at some point reverses. So I would like to know that you need the trends to also be able to know where to invest your effort. Should you focus on this architecture, algorithm, or it will not be used in the future because at larger scale it will not be the tool of choice. Also, one step kind of in more general direction. If you think about that, and there is this nice book, Scale, and essentially it talks about scaling in networks, or well, more generally, you can say dynamical systems, way beyond AI, nature, societies, economics, everything. So there seems to be, like you think about that, emergence of complex behaviors with scale. Of course, the differences are how things scale, what is the network dynamics, what type of communication between nodes, but all kind of intelligent behavior, whether in nature or at the level of society, seems to emerge from network of interacting components at particular scales. I will not dive into details, but it is a really interesting book, kind of puts things in the perspective as well. And talking about scaling laws, I might just give like very brief history and outlines like how it's usually done. I mean, more classical or empirical scaling laws that probably many of you know about. It's, I would put in so-called closed box prediction category, where you observe perhaps somebody else model behavior, like I don't know, here's like a GPT model, so somebody, it's not your model, you don't train it, you don't have access to internal, say, training dynamics, you cannot do interpretability, but you see performance and you know the size of the data and so on. So you can try to, just using that information as closed box, make predictions about that model and how performance and other properties, which is very important, not just performance, whether it's robustness, whether it's truthfulness, whether it's anything of interest or kind of AI safety and alignment, whatever metric. You can try to predict that. If it's your model or you have access, you can be much more informed, and then you can combine the patterns in the kind of training by looking at laws, activations, weights, and how they evolve, and that can be aiding information towards predicting the future behavior of such things. So I'm assuming everybody has seen the famous 3 straight lines on the local plot. There is even a t-shirt that we're joking about, which actually was popularized by one of my students. Long story. There was lots of Twitter discussions about that, but so the t-shirt was pretty much with this picture. By now, of course, this is Jared Kaplan and the colleagues' old 2020 papers. I think it was winter or spring 2020 when the paper first came out. That was surprisingly simple closed box type of prediction of behaviors, where essentially a very simple functional form of just power laws, which correspond to those straight lines with plot and log, can be apparently fit and extrapolate to extent to, again, test laws or validation laws of models. So it's not necessarily going to work if you're interested in measuring particular metrics of interest. It will be on test laws, and that's a story. So like, it was interesting that, okay, so now you can compute those trends, you can compare methods, you can compare whether your architecture is better than other architecture in the long run, and you can hopefully, predict where to invest your compute and how. Then there were also observations that it doesn't have to be transformer to show scaling laws. It could be as simple as multi-layer perceptron. So pretty much it's not as maybe efficient of the scaling and not as good of the scaling exponent, but it does scale eventually. And if you have infinite resources, maybe you can scale it to the good enough performance too. So like, and again, step back, it's not the first time that scaling behaviors in neural networks were observed. It goes back to like at least 1994, Rish, back then it was called Rish paper, by Irina, Vladimir Vapnik, and other big names. Actually, it was, to the best of my knowledge, the first paper that showed that neural network performance with respect to amount of data growing on the x-axis, it's also local code, follows power law. So that was kind of a first data-related power law paper. I don't know, maybe there was something before that. And then, of course, there was a whole history of Joe Hessman's paper when it was extended by orders of magnitude for larger networks. Basically, it was extended to also x-axis being model size, not just data. And then basically the Kaplan scaling laws where also the compute on the x-axis was shown to have like similar power law behavior. Again, that was, we'll talk about the extensions of that more recently later because that was a bit of a history. And then a few years later, 2022, chinchilla scaling laws. So paper comes out questioning the compute optimal power law from the Jared's paper. And essentially, like if you properly kind of do hyperparameter tuning and so on, you can show that, okay, so you can have scaling law with this functional form, but essentially the lesson was that you can go with much smaller amount of parameters, but much larger amount of data, and you will reach similar performance. And that was kind of a plot at that point showing how that chinchilla model, in terms of number of parameters, but number of data compares to other kind of state-of-art models. So that was a lesson, like shift your attention to more data and invest compute differently. So essentially, in the original paper by Jared Kaplan and colleagues, suggestion was to invest more in growing the model size, like 2 to 5 data versus model, and Chinchilla showed that the compute optimal will be roughly 50-50. Again, compute optimal was assumed to be the training compute. And that was kind of demonstration that, you take very large, at that point, Gopher model and much smaller Chinchilla, but you train on 1.4 trillion tokens, 300 billion tokens, and your loss, your validation loss, will be pretty much the same. So that was, for a couple of years, state-of-art in scaling laws for optimizing compute at training time. And then recently, I'd say starting with Llama and subsequent versions, people started shifting the focus toward inference because in practice, especially with sufficiently large models, if you want to serve multiple customers, constantly kind of asking questions, your model, whether it's even GPT-4 and so on, you have significant kind of amount of compute spent on answering those questions. And understanding how the inference time scales is very important because it's becoming like more and more costly. So that's kind of a post-Chinchilla era. I'm still kind of giving the history overview here, but feel free to interrupt at any moment. Bottom line is that there is more and more shift in this direction. Initially with more like practical models like Llama using more data and more beyond Chinchilla optimal and getting smaller models with comparable performance to much larger ones. There are inference scaling laws papers appearing this year. There were like several in this direction. There are various attempts to also improve inference time compute by making models compressed or quantized. There was this whole area of post-training model quantization and compression, and more recently, training models that are already low bit. And we added our 2 cents by training on Summit supercomputer last summer. Took quite a few months, a suite of models that are actually ternary, and we're now training like 4 valued and so on and comparing them. I'll talk about that a bit later, but it's a promising direction too, which kind of allows you to train models that will take much less memory, and they promise to also improve your latency and have much faster inference, although you need to implement specific kernels for that. So various approaches to the problem of inference costs. So that's simply where we are now. Back to basically the bullet points from the item list. Yeah, so a couple of years ago, first it was Llama. Llama said, okay, so let's go beyond chinchilla optimal in terms of data, and let's keep basically training more and more, spending compute during training, not optimally, but saving later on the inference. And this training continued, and the interesting thing is, those were like the old Llama 2 models. What was shown that you keep increasing the amount of data way past that chinchilla optimal, you don't see any signs of saturation, which kind of raises a question like how far can you go, how much more data you can feed to llamas before they are unable to kind of absorb more and so on. So this was, as I said, the alternative approach I briefly mentioned. I apologize, I only kind of briefly mentioned various topics and hope that we can discuss them later on in more detail if there is interest. Yeah, so the promise of quantization of trained models at low bit widths, basically it's a great submission. But anyway, so it's already on open review and on archive, so you can find more details there. It's quite promising in terms of trade-off between bit size and performance. This green one that grows fastest, like almost like that, compared to floating point, just the regular kind of precision models. And also, interestingly, it's better than in terms of the performance versus a bit size trade-off than the models obtained by usual post-training compression, like 3-4 models. So it seems to be better to actually train quantized model from scratch than quantize it later on. And in terms of scaling laws, it looks like conclusion is, while at lower scales, the floating point for the same model size may be still better than quantized, the curves kind of converge, and it seems like if you still large model sizes, quantized models will start outperforming floating points. Yes?
If you leave the amount of bits constant, but you shift allocation between depth of parameter weights versus number of parameters, like what, is there any research there on what?
That's a good question. It's kind of relatively new stuff. There was BigNet. Then this thing that we were started doing like this year with ternary. But I think it's a very promising area that needs to be really explored. And the question you asked, yeah, I mean, there are many ways to possibly improve it. Yeah, there is also a recent paper, like, well, we put some of the preliminary scaling laws in that paper and kind of working on that. There's also recent paper on scaling laws for low bit models, but it only investigates what happens like below 1 billion. So it's relatively limited. And just as majority of scaling law papers, interestingly, people fit whatever functional form, quite often power law, chinchilla, and so on, but people do not show how their functional form will extrapolate, which is a bit funny because any statistical person reviewing such scaling law paper will say, guys, you think without testing for extrapolation, how it will really generalize. So that's why we don't know. I mean, it's promising to see that people started looking into this area, but I think like I'm inviting people to actually do more research there, because I think it has quite a bit of promise, and needless to say, for any kind of edge devices that people are interested these days, that might be a way to go. Again, people did compression and quantization for last several years quite a lot, but it seems like it might be better to just train models from scratch at low bit widths. Yeah. To be explored more, like if you're interested, I mean, the paper is on archive, and I think most updated version. But anyway, so it is I was just kind of describing this whole idea of improving inference time, compute, and inference time savings, basically throughput latency. This is one approach. There are also others which do not go into low bitrate models, but try to see what happens if you just invest in more data training time. So this was a ICML paper last summer talking about trade-off between compute during training, compute during inference. And roughly speaking, the idea there was, you look at how much it costs you to train smaller models, like 7B models in this case, on more data versus larger model on less data. You have your chinchilla optimal points, but this optimality is only for pre-training. Then, during the inference, your smaller model will make it up in terms of savings because it will provide you with faster inference, less compute, and basically it was like a schematic picture in their paper saying that you can achieve a better trade-off, and overall, on the right, your small model trained on more data that wasted training compute. Overall amount of compute will be saved if you have sufficiently many queries during the inference time, and it looks like the amount of queries will only be growing because people are working with those systems non-stop. So anyway, that was an example of the papers looking into inference time compute. They also were investigating, that was an interesting study where they tried to compare their scaling laws with chinchilla scaling laws. And they realized that if you only fit relatively small or classical number of tokens per parameter, like chinchilla paper suggests, or even like what Llama does, you will be like in this region. And when you fit like chinchilla scaling laws to their functional form, it will severely overestimate the effect of additional data. So curves will be straighter, but in reality, especially if you look at the actual data points, they just kept feeding more and more data. The curves are flattening, not going straight or even like that. So the interesting thing is, bottom line with all these scaling laws is that none of them are perfect, and they only extrapolate well in certain regimes. Definitely things get more complex than just power laws and even chinchilla laws, and even in some cases it's an open question what kind of functional form could even possibly fit and extrapolate this type of behavior. So that paper asked this question, which immediately made me think about something I'm going to talk in a few slides from now. There are certain functional forms that are trying to capture that. Yes?
So these different functional forms can fit the historical data, increasingly well. But to what extent can they give insight to what's actually happening or why this is happening? Because even though it's called a law,
it's a quote unquote law.
It's a quote
unquote law.
So have we understood why it's happening and therefore have confidence about whether it'll happen next year or 5 years from now?
Yeah, so that's of course a tough question. I was going to talk a little bit about if you have access to the model you're training, so it's not somebody's model you're just trying to predict behavior, but you can actually see learning dynamics. You can do whatever form of interpretability. It doesn't necessarily have to be mechanistic interpretability. To me does not equal sparse open encoders. It's just a particular type of thing, plus it's during inference. I would say more generally, mechanistic interpretability could be investigating any kind of patterns during training and inference that may give you information about future behavior and changes in that. But it's tough. It's an open area. Of course, fitting curves is relatively easy. Plus, it was surprising that it works at all. That there are relatively simple functional forms that seems to be sufficiently accurate to fit it. Yeah, like even the fact that power laws were to some extent working at all was okay. Wow. Yeah.
So does anyone have like a conjecture of why you would expect that the error would improve if you increase the portions? Is there some like underlying?
To be honest, yeah, there are various more like theoretical papers, especially recently, and like from dynamical system perspective, there are like more statistical physicists looking into that. There are also studies, especially of predicting behavior that changes rapidly, like grokking. I was going to talk about that a little bit. And so basically that's what the focus of this type of study is, trying to understand what properties of trading dynamics can relate and why power laws in some regimes, when regimes may change, and so on and so forth. So it's actually a whole body of very recent literature, I would say literally like maybe past year, that tries to explore that. Yeah, so probably I won't be able just to give you the overview of the whole thing, but there is definitely a list of papers I would recommend, and I need to read them myself. Yeah. And as you know, once statistical physicists go into machine learning field, lots of interesting things happen. And but bottom line, I think, is for now, what we can say that I was going to talk about this a little bit. Roughly, it seems like many behaviors can be captured by a combination of regimes where you approximately power law, and then regime changes for some reason, and you have maybe smooth change, and then there is another one, and so on and so forth. So this is again purely empirical. Understanding the mechanisms is ongoing work. Anyway, and that's about what I kind of wanted to say, that all these power laws historically were nicely kind of obtained for one metric of performance, like test laws, validation laws. And once you start measuring other metrics, even the classification errors and so on, I know there was also a paper about whether the emergent behaviors are a mirage or not, and the answer is not quite and not always. Even the original GPT-3 paper, after kind of doing the usual analysis of test laws, seeing power laws, on particular tasks, like downstream tasks like arithmetic, that plot on the right, it was observed that, interestingly, there is some kind of quote-unquote phase transition. Oh, I hope there are no statistical physicists in the room who want to just burn me alive for using the term. That's why I say quote-unquote. I mean, not phase transition, but some sharp change in behavior. Yeah, call it whatever.
Statistical physicists might be the biggest abusers of the word.
Bottom line, that was kind of one of the first examples where people say, oh, interesting. So up to a certain model size on x-axis, GPT-3 cannot do 2-digit, 3-digit, 4-digit, whatever arithmetic. After a certain model size, it starts, quote-unquote, getting it or grokking it. And the harder the problem, like more digit arithmetic, the later it happens. Good question, why? Then there was, next year, this workshop paper, that's a clear workshop, where there was this grokking story. The famous grokking story when I think it was just an accident of not killing the crosses at the right time and letting it run for, extra days or whatever, and then suddenly it groked it was a modular arithmetic problem in that particular paper. First it kind of groked it on training data, plotted them on test data. That was interesting, and that pretty much generated the whole recent ecosystem of papers exploring specifically grokking on modular arithmetic. So you can only imagine how happy the statistical physicists were to see such a behavior. We had scaling workshop. We started students got very excited. We started having scaling workshops initially locally in Mont Tremblant back in October 2021, and Jared at that point already at Anthropic was still not too busy, so he was able to pull in and spend 3 hours just brainstorming stuff with students. It happened a few more times and then he got busy. Yeah, but that's type 2 phase transition. It must be. That was an interesting discussion and so on. So what I'm trying to say that there are more recent kind of papers about emergent behaviors were showing that it's not always straight lines. Behaviors may change abruptly. Why? To be figured out in each particular case as a function of what? Just the compute the number of steps, as a model size, data, so on and so forth. And it's not the first time we see transitions in machine learning or computer science, because in good old constraint selection problems and optimization, people observed that long time ago in physical stability problems, and the relationship was with phase transitions in random graphs. And the interesting frequent collide theorem saying that if you have any property of the graph that's monotonically increasing or decreasing in terms of probability with edge addition, it will experience phase transition. But linking that to transformers is a bit complicated. Anyway, I have 5 minutes left, so I will have to stop working. Okay, so okay. Thank you. Once I said that I have 5 minutes left, I think my laptop got scared and started freaking out. Again, we should anthropomorphize or not. Anyway, yeah, but it's hard to resist. So, come on. Okay. Okay, so yeah, I really have to speed up, but there is another interesting story. It's our recent paper of trying to measure other metrics, like the space of metrics that you can imagine for which you would like to obtain scaling laws is anything from usual classical performance to any other interesting metrics, in this case for like psychological metrics of like certain traits that you can obtain if you do personality tests on LLMs. I don't have time to go into details, but bottom line is there are very interesting and very non-linear types of scaling that you can kind of explore depending on the prompt. Like you prompt the system to be useful assistant, Buddhist monk, depressed person, schizophrenic person, and you get very different type of scaling. It's definitely non-linear, and there are some interesting comparisons here, like the good properties of assistant actually improve, and like neuroinnocence go down with model scale. But if the model was prompted to be depressed, opposite things happen. There's lots of interesting stuff, and the open question is like, what kind of scaling laws and function form could possibly feed that? So regarding grokking, yeah, we had this paper last year where we essentially saw some type of patterns. Back to your question. Again, could be much more, but there was some interesting analogy between high frequency oscillations in loss that, again, empirically, practically always precede transition. And if you don't see those oscillations, you don't see the observed grokking. An analogy is with medical systems that happens like in epilepsy before the event, and in some other kind of phase transition situations in nature, so that's where inspiration came from. Then if you don't have this information and you do want more general functional work, that was like also our work from, actually last year. A combination of smoothly connected power laws seems to be quite generic functional form, covering pretty much all the pieces that we receive in recent papers reporting scaling of whatever properties in whatever type of models and whatever modalities. So pretty much that broken neural scaling, those papers purely empirical, but shows quite useful family of kind of functional forms describing pretty much scaling of anything you might be interested in. Anyway, so it was actually even able to predict transition if the stars align, there is not much noise in the data, and close enough to transition, and transition is not too sharp. Anyway, so it's probably time to wrap it up. and ask questions. I think we will get to the very last part, that what's next? Of course, these scaling laws do not take into account many things that they probably should. They should be perhaps relative to things, not just we can control, data size, model size, amount of compute, but things we cannot control. What's the complexity of that kind of downstream task? Clearly, scaling laws should depend on that. Like when people say, I want to create a model to continue learning later, if it's a few rotated and missed problems, we probably don't need as large of a model trained on as large of data as if it is, I don't know, sending robot to Mars and having truly continual learning with very diverse environments and many of them, or even playing various online video games. Complexity of downstream tasks should be somewhere in scaling laws too, and many other things. And wrapping it up, I just wanted to mention that despite being in academia, we're kind of lucky to get some compute on the US government supercomputers like Summit and Frontier, which allowed us to train that Spectre suite and kind of many other things over the past 2 years. Some language models, some jointly with Together, and Coursera, and AGI, some other things on our own, and the work on compression is still kind of ongoing, as well as continual training. Anyway, and I wanted to talk about the cost and potential alternative to transformers, which is totally open-ended discussion with potential inspirations from not just neuroscience, but basically biology and science of scaling networks of cells and so on and so forth. So where you will need to find the proper architecture that will give you enough capacity and hopefully very good scaling exponents, which perhaps might be better than what we have now, and maybe they will be more energy efficient. But that's, yeah, it's open-ended. Okay, I think I'm really out of time. So I guess we should probably switch to questions now.
Yeah, if anyone has questions that they want to drop in the Discord, I will prioritize the most upvoted ones, but since it's a pretty small group, you can just raise your hands too.
Have you heard much about the recent pre-training run failures different labs have been having, and what do you think the causes are? Is it they're trying to do too many modalities into one model, or is it just scaling the hardware infrastructure? Like, give me thoughts on some of those reports that have been coming out.
So can you just repeat what about different modalities?
Going from just text and image to maybe like 5 modalities, in a like style.
Yeah, so it's okay. So by the way, yeah, it's indeed. I mean, going beyond text and image is happening a lot. By the way, there is, I think, lots of interest in training time series foundation models. I didn't even get to talk about that, but so we are working on that. We had like a small Lag Llama foundation model back in February. Well, I mean, it's tiny. It technically can be called foundation model because it was trained on large variety of diverse data, and it does kind of generalize out of distribution a few short. But then, of course, there were like all the Cronus models and so time series modality seems to be now kind of GPT-3 moment for good reasons, because time series are everywhere, not just finance. They're in science, they are pretty much anywhere, so any kind of transactional data, time series, so you can imagine Oracle and so forth. Everyone wants time series foundation models. So, and yes, so that's happening. And by the way, interesting things happening. We're kind of looking into that too. And there is some promising literature transfer across modalities might be happening. And it's really, I mean, it doesn't always happen. The question is when and under what conditions. And from our current experience, you can try transfer. There are scaling laws for transfer, but they were applied only switching from English to Python. It's not quite a huge distribution shift. Say if you try to switch from language to time series, we had a paper in workshop recently, like switching from pre-trained language models like T5, Cronus, Cronus is time series foundation model, but architecture is same as a corresponding language model T5. It does transfer to EG, for example, so you get a good head start. But if you try PTR, it doesn't. So transfer is not just from modality to modality, it really, I guess, depends on quality of the underlying, say, language model. And you can actually start thinking that maybe it's not that surprising because it doesn't matter what modality is. After you tokenize, of course, depends how you tokenize, that matters. You get a sequence of tokens and you're trying to find the basically conditional probability distribution of the risk model. And maybe, hypothetically, there is some space of common distributions that multiple modalities can be mapped to. Depends how you map them, which is determined by the model you use. So that's why maybe some models can transfer better than others. But I don't know if I was kind of answering your question or rather going a bit of tangent, but the question whether expansion to different modalities is happening and why, yeah, definitely, because there is lots of demand for this type of models, and whether you can kind of reuse existing models, hopefully, at least some of them. And then you also mentioned something about hardware, which
it sounds like a lot of pre-training runs are failing. So is it because of the multimodality being a hard problem to do that mapping, or is it more just doing it with the hardware at scale and it's more of an engineering problem? So
yeah, I'm trying to think like in what sense also pre-training is failing. I mean, things often also fail just due to hyperparameter. I mean, it's so potentially sensitive to hyperparameter tuning that, even if you have something like mu-p type of approaches to extrapolating hyperparameters, it's not enough. I mean, So I guess answering the question why a particular kind of training run doesn't give you a good model, and whether, hyperparameter is one thing. I think data matter a lot. And suspicion about, say, PTA versus T5 and transfer is perhaps not so much in architecture, but perhaps the quality of data set. And absolutely kind of exact answer is like we don't ever know anything for sure, but there are, I guess, such intuitions. So I think the quality of data set matters to a large extent. And I don't know.
Got one. So the traditional scaling laws are usually about data, compute, parameter size.
Right.
It sounds like a lot of people are saying that pre-trained scaling is leveling off, and now we're in a new paradigm of scaling, such as inference time compute.
Right.
Do you believe that to be the case? And if so, are there any other new paradigms that you think are on the horizon?
Yeah. So we kind of talked about that a little bit. I don't think the training scaling laws are completely leveling off, but now they're being combined in terms of trade-off with the inference time. So I think like this example of the paper that I mentioned, basically trying to come up with scaling laws that will take into account the inference costs. That's a good example. Then there are a few more, of course, in the context of much more time spent on inference, like in the O1 systems like that. So that becomes really a new interesting field. Yeah, I mean, you could say that pre-training scaling laws is quite separated, even though it's not fully solved, I would say. So I would say there is a shift, but maybe not replacement. So it will be more about combining both costs. You cannot completely ignore pre-training costs, and you still want to understand for any of these type of models, scaling of interesting behaviors and properties. And that's why when I was briefly talking about broken neural scaling laws, the nice thing there was it was not just about predicting loss or accuracy. It was about predicting a whole bunch of different metrics that you can keep inventing and that could be of interest with respect to safety of system behavior. You want to predict that, not just loss. And that is a property of that pre-trained model, and that you still would like to be able to capture. So inference cost is one thing, but ability to accurately predict various interesting and potentially dangerous behaviors is still in the kind of realm of pre-training scaling goals. Just the y-axis is different, and you need to see whether your methods will properly model them. Yeah. So I would say, yeah, there will be lots of developments in inference time, compute, and cost, while still I think we should push for development of methods that accurately predict behaviors beyond just capabilities. Yeah, and that is still kind of pre-training scaling laws of different companies. Yeah. Other questions?
Okay, I have a capabilities question. Do you think that we have formalized the definition of capability properly enough? Do you think there's more work in terms of how we think about capabilities?
Yeah, I mean, in a sense, like if you approach it from like one perspective, you could say it's all behaviors of some complex network. Whether it's from fastness or truthfulness or psychological kind of rankings on particular tests, or it is accuracy on predicting something, or this and that. They're just behaviors. What you call capability and what you call alignment is more like a human-imposed condition. You can just say, here is a complex dynamical system and it has multiple behaviors. You can try to understand how they develop, how to predict them, but with respect to you, you separate them and capabilities and alignment to some extent. Again, I know that this question was debated quite a bit because, I mean, is it really orthogonal or not? I don't think it's absolutely has to be orthogonal. Like the alignment, behaviors, and properties and capabilities do not have to be necessarily orthogonal. But the only true answer would be like you need to see data. Yeah. So yeah, I think this division is somewhat artificial sometimes. Yeah. But yeah, I know many alignment people say, don't say that alignment metrics are capabilities. Yeah. And then we can have a long discussion for the next few hours.
We have time for one more question. All right, give it up for Irina. Thank you.